Okay, so welcome again to today's PGSS talk. We're going to be hearing from Carsten Peterson, who is a PhD student at Michigan Math, working with Ralf Spatzier. So yeah, I'm really excited to take it away.
All right, yeah, thank you for the introduction. It's interesting for me giving this talk because, as someone in the math department trying to learn some physics and then trying to explain physics to the math people, but now I'm doing the opposite because my project, it doesn't necessarily use quantum mechanics, but it's inspired by a lot of ideas from quantum mechanics. So it's a little bit of a flipping of the script trying to explain math to physics people. So hopefully, I might use language that's maybe different than the way physicists describe certain things, but hopefully not too much is lost in translation. So the title of my talk is Quantum Ergodicity on Manifolds and Graphs. And yes, that quantum is like quantum in the sense of quantum mechanics. All right, so let me first introduce what's known as the geodesic flow, which occurs on a manifold. Okay, so again, I'm not entirely sure what a typical physics grad student knows, but I'll try to at least give the intuition for most of the objects I'm going to deal with. A manifold is a space which, at least locally, looks like a copy of R to the n. So R to the n is kind of your model space. And you should think a manifold is something that is glued together from pieces of R to the n. So that means for every point on your manifold, like here I've drawn this two-hole donut, I can find a ball around that point that looks like a ball in Rn. And on a manifold or on a smooth manifold, every point has what's called the tangent space. And what that is intuitively is essentially the space of arrows emanating from your fixed point. And the tangent space is a vector space. Sometimes, so there's sort of abstract manifolds, and then you can put extra structure on manifolds and they have extra properties. So one of these structures is called a Riemannian metric. And then you get what's called a Riemannian manifold. A Riemannian manifold means that on each of these tangent spaces, which these are vector spaces, you have what's called an inner product, which basically it's a dot product. It's a way of dot products of these vectors. And once you have this, so I should mention, like at every point you have your own dot product. But once you have this, it allows you to define more geometric structures on your manifold, such as distances between points, angles when curves meet. You can talk about the angle that they meet at. You can talk about volumes of regions. You can talk about curvature, which is kind of hard to define, but a very important concept, among other things. And here I have a picture of two different tori, donuts, that are the same manifold, but they're not the same Riemannian manifold. So here, okay, this is a donut like we usually think of a donut when we picture it. And here is sort of a different way of drawing a donut. Maybe you've seen this before, but you should imagine what these arrows mean is like, if I were to travel in this space and I were to go here, then I would just end up going back here. And same if I were to go here and keep traveling in a straight line, I would just go back here. So people often talk about this. It's like a Pac-Man screen. In Pac-Man, if you go off the screen, you come out the other side. So these two are both the same manifold in the sense that they're both tori. So you could say that these are, in mathematics, we'd say they're diffeomorphic, but they're not the same Riemannian manifold. So they're not what's called isometric, which means like if you were to actually measure distances on these two different manifolds, you would get different results. On Riemannian manifolds, a really important concept is that of a geodesic, which is a path connecting 2 points on the manifold, which is sort of the shortest path possible, or at least it's locally the shortest path possible. So again, the Riemannian metric allows you to measure the lengths of paths. Here I've drawn the sphere, and if you consider this is supposed to represent a great circle on the sphere, and if you have these 2 points, then there are several geodesics connecting these 2 points. So there's this geodesic, which again, this is going to be the shortest path connecting them, but this one is also a geodesic, even though it's not the shortest path. At every moment along this path, you are sort of locally minimizing the distance. So the distance from here to here, that's the shortest path between them. And from here to here, that's the shortest path. And you can glue those all together and you get a geodesic. So in this case, we see this geodesic actually closes up, which is very exceptional. That doesn't typically happen. So more generally on a manifold, if you choose a point and you choose a direction, this determines for you a unique geodesic. But these geodesics can be very complicated. In general, they won't close up. So here I've tried to demonstrate kind of the level of complexity you can get. The geodesic could sort of wander all around the manifold. So you should imagine this is like wrapping all around. But again, to specify it, I just needed to choose a point and a direction. So something that when you're dealing with geodesic, an object that's really useful to talk about is what's called the tangent bundle. And I guess in physics, maybe you might call this phase space, essentially. It's essentially the same thing. So the tangent bundle of a manifold is the space of all points and choices of tangent vectors at those points. But it is itself a new manifold, a bigger manifold. So a point on the tangent bundle would be like something like this. You should imagine a point plus an arrow from that point. And on the tangent bundle, we define what's called the geodesic flow. So this G of t, you should mean it's like a transformation of the tangent bundle to itself that should be thought of like the geodesic flow for time t. So given a point P and a tangent vector V, this gets mapped to move along the geodesic determined by the point P and in the direction V for time t, and then see what is the new point you're at and what is the new direction you're pointing in. And so that's going to be the image of this point under the flow for time t part of the geodesic flow. Okay, so that's the geodesic flow. And now I want to give another perspective on the geodesic flow that ties more closely with physics and with classical mechanics and ultimately also with quantum mechanics, which is sort of the Hamiltonian perspective on this stuff. So, okay, the tangent bundle, in general, if you have a manifold on the tangent bundle, you have this extra piece of structure that is pretty exceptional called a symplectic form, which I'm not going to define, but what the symplectic form does for you is it gives you a way of converting functions on the tangent bundle, so a function that depends only on your position and velocity, into a flow on the tangent bundle. And I think in physics, they would call these Hamilton's equations, but there's sort of this whole symplectic formalism that works in a lot of generality. And a very natural, and often we call these functions Hamiltonian functions. So a very natural Hamiltonian function is if you take a point and a tangent vector at that point, you measure what is the size of that vector with respect to the dot product at that point. What is the norm squared? Or maybe what is 1/2 the norm squared? So it's basically like, you should think of this as like 1/2 mv squared. It's like kinetic energy in physics. And if you go through all of this Hamiltonian formalism, you get a flow. What flow do you get? You get the geodesic flow. And in a lot of ways, this is very much like what happens in classical mechanics. Essentially, we're almost like constructing a classical mechanics on the manifold. It's like saying in the absence of any potential energy, so here this only has a kinetic piece, then motion is just straight lines at constant velocity, namely move along geodesics. Okay, so now I want to introduce the concept of ergodicity. So before I mentioned, if you consider a sphere, any geodesic you choose is going to close it back up to itself. Namely, these are the great circles on a sphere. But that is really exceptional. Ergodicity is sort of like the opposite phenomenon. It's saying that if you choose a generic geodesic and you follow it for a long time, then the amount of time that the geodesic spends in any given region of the manifold is proportional to that region's volume. So you should picture something like this. So this picture is kind of a cartoon. This is supposed to be like a 2-hole donut, if you can see. You've fixed some region, this yellow region here, and you've chosen some geodesic and you let it run for a really long time. It's going to go everywhere in this kind of crazy way. And then you measure the proportion of time that the geodesic spends inside of this yellow region. So that's what this quantity represents. And you take the limit as you let the geodesic keep going forever. And in the limit, what you get is a quantity proportional to the volume of the region. So here, if you normalize so that the volume of the entire manifold is 1, then this is exactly what you'll get, the volume of that region that you've chosen. And you might wonder, like, well, how can you know if the geodesic flow is ergodic? So when you have a Riemann manifold, there's something you can define called curvature. I'll say a little bit more about later. And if the curvature is negative, it turns out that the geodesic flow is ergodic. And a really important class of manifolds with negative curvature are the ones called hyperbolic manifolds, which I'll also say a little bit more about later. So now I want to introduce some quantum mechanics, at least from my perspective. So there's this procedure that allows you to convert functions on the tangent bundle, which you might call classical observables because they only depend on position and velocity, into operators on L2 of the manifold. So L2 of the manifold, these are functions on the manifold taking values in the complex numbers for which when you integrate the norm squared, you get a finite number. And often these operators are what would be called quantum observables. So if you start with the real valued function on the tangent bundle, you can show you'll always get a self-adjoint operator acting on L2 of M. And in general, this procedure is known as quantization. And there are actually different ways of doing it, but they're all sort of roughly the same. But when you do this procedure, you essentially have to choose a value of this parameter h, which to a physicist, h is just, oh, it's Planck's constant. But to a mathematician, you should think h is some small number that we can choose whatever value of it we want. And for each value of h, we get a different quantization scheme. So when we take our Hamiltonian function before, namely like kinetic energy, and we go through this quantization procedure with our choice of h, we get a Hamiltonian operator, which in this case is going to be h squared times the Laplacian. The Laplacian is an operator that you probably have all seen, and often it's presented in coordinates, but I want to describe geometrically how to think about it on a manifold. So if you have a manifold M, the Laplacian is really a measure of how much a function varies, how much the average value of a function on like a small ball centered at a point differs from the actual value of the function at that point. So you should imagine, like, if I have some function, I want to take the Laplacian of that function, then I look at the value of the function at my point here, and I look at the value of the function, the average value on circles that are getting smaller and smaller, and I kind of want to see and how does that average value on small circles differ from the value of the function at the point. And there's a way you can kind of phrase this in terms of derivatives, and this is a geometric definition of the Laplacian. You can also give, like, in coordinates, you can give a definition that's more computable, but this is a good geometric picture of how to compute the Laplacian. Instead of the geodesic flow now, what we have is the Schrodinger equation. So we have these wave functions psi that evolve over time according to the Schrodinger equation. And the Schrodinger equation is a linear partial differential equation. And that means you can solve it by essentially diagonalizing the Laplacian, namely finding the eigenvalues and eigenfunctions of the Laplacian. So I'll just mention that if you have, it's a fact that if you have a compact manifold, then the Laplacian has discrete spectrum and non-negative spectrum. But really what that means in practice is that the eigenfunctions of the Laplacian are actually themselves L2 functions, which is not always true. And when it is true, it makes the analysis a lot easier. So if you want to solve in general the Schrodinger equation with some initial condition, what you can do is you take your initial condition at time 0, you decompose that function in terms of the eigenfunctions of the Laplacian. So that's what this represents. So this right here, you should think of this as the eigenfunction with eigenvalue lambda j. Then the solution to the Schrodinger equation with this boundary condition, all you do is you essentially take this decomposition and you throw in these factors e to the minus ih lambda jt. Hopefully I got this right. Maybe this is a positive, I'm not sure. I think this is correct, but it might be slightly wrong. There's also the issue of interpreting what this wave function actually represents. So in classical mechanics, we often think of the wave function as sort of giving us the probability of measuring a quantum particle in a given position. So if I were to fix a region on the manifold and I were to integrate the norm squared of my wave function, I interpret that as the probability of detecting the particle in region R at time t. So in the case that we have a eigenfunction of the Laplacian as our initial condition, it's already an eigenfunction, then the wave function of evolution according to the Schrodinger equation, you're just multiplying by this factor e to the minus ih lambda jt, whose norm is always 1. So when you look at this quantity psi xt squared, it doesn't depend on t. It's just equal to this eigenfunction of the Laplacian squared. It's independent of time. So in some sense, you could think like the particle is stationary in the sense that the probability of detecting it at any given place like doesn't depend on time. And we also can interpret then as this particle as having a definite energy, namely the eigenvalue with respect to the Hamiltonian operator. So if I have this kind of equation here, then I could think of this as a particle with energy h squared lambda. Okay, so now this is maybe the most technical thing I'm going to say. Hopefully this makes sense. So if you have an eigenfunction of the Laplacian with eigenvalue lambda, then we can think of this as representing a stationary particle with energy 1 as long as we judiciously choose the value of h. So if we set h equal to 1 over square root of lambda, then this quantity h squared lambda becomes 1. And now imagine we have a sequence of eigenfunctions with eigenvalue going to infinity, lambda going to infinity. And we keep rescaling h so that it's equal to 1 over square root of lambda. Then we have a sequence of stationary states with energy, which is a constant equal to 1. But now lambda going to infinity implies that 1 over square root of lambda goes to 0. And at least sort of, there's this classical quantum correspondence that tells us that if we take h going to 0, then we should somehow recover classical mechanics from quantum mechanics. And that's where quantum ergodicity comes in. So what does quantum ergodicity say? It says if you have a manifold for which the geodesic flow is ergodic, and you have a sequence of eigenfunctions of the Laplacian with eigenvalue going to infinity, then if you choose a subset of the manifold, R, then for most choices of these sequences of eigenfunctions with eigenvalue going to infinity, and every choice of region at the limit along this sequence of the integral of the norm squared of your eigenfunction over your region, that will converge to the volume of the region. And maybe I'll just mention in passing that in mathematics, this type of convergence, really, this is like a statement about convergence of measures, but there are lots of topologies on the space of measures, and this is what's called weak star convergence of measures. But if I were to interpret this statement, we should think about like saying a generic quantum particle is equally likely to be found everywhere on the manifold in what you might call the high energy limit, namely letting lambda go to infinity, but what's also sometimes called the semi-classical limit, which is like letting h go to 0. And you should compare this to the statement of ergodicity, which says that a generic classical particle moving in a straight line is equally likely to end up anywhere on the manifold as t goes to infinity. So that's quantum ergodicity. It's a proven theorem. There's the conjectured strengthening of this theorem, which is that the above statement is true not just for most sequences of eigenfunctions with eigenvalue going to infinity, but for all sequences. And this is known as quantum unique ergodicity, and it's been proven for special classes of manifolds known as arithmetic hyperbolic surfaces. And the person who proved that actually won the Fields Medal partially for that result, and it uses like a ton of different tools. It's a very complex result, but synthesized a lot of ideas. So now I'm going to switch gears a little bit and talk about hyperbolic surfaces. So in the background of all of hyperbolic surfaces theory is this group SL2R. SL2R is the group of 2x2 matrices with real entries for which the determinant is 1. And what's important about SL2R is that it acts on what's called the Riemann sphere. So the Riemann sphere, you should think of, it's like I took the complex plane and then I added a point at infinity, and it kind of just closed up the complex plane into a sphere. It's like topologically a sphere. You'll sometimes see it also written as C union infinity. So I've like added a point at infinity, but it's also another perspective. It's what's called a projective line over the complex numbers. And the way that SL2 acts is by what are called Mobius transformations. So this matrix is going to determine a transformation of the Riemann sphere according to this formula. And you can show that this action preserves the part of the complex numbers with where the imaginary part is positive, known as the upper half plane. But what's more is that this action also preserves a certain Riemannian metric on the upper half plane, which, so here I've written this formula, dx squared plus dy squared over y squared. So how you should interpret this formula, it's like if I'm at a point in the upper half plane and I take a vector, then I look at the coordinates, like it's x plus iy coordinates, and I look at the length of this vector, if I just thought of it as a normal vector and the normal way of measuring lengths of vectors in R2, but then I scale it by a factor of 1 over y squared. And that's my new way of measuring the size of vectors. You can show that geodesics in this context correspond to half circles which meet the real axis orthogonally. And it's a little bit weird. So because I have this 1 over y squared, that implies that as I approach the real axis, like if I had a line segment like this versus like this, down here closer to the real axis, that line segment is way bigger. And once I actually have reached the real axis, that line segment has infinite length. So all of these like half circles, even though they look like they're finite, they actually have infinite length in the hyperbolic metric. Another way of representing the hyperbolic plane that is also useful, and maybe for this talk is more useful, is what's called the Poincare disk model. So there's sort of a way you can transform this upper half plane through what's called a conformal map. You can turn it into a circle, and then you can kind of conjugate this SL2R action to act on the circle. And in the circle context, geodesics again correspond to circles that meet this red circle orthogonally. Okay, but what does that have to do with hyperbolic surfaces? So SL2R is this big group that acts on this space, but this group has subgroups, and there are certain subgroups which are called lattices that are these discrete subgroups of SL2R. They act on the hyperbolic plane, and then it's possible to quotient by this action to get a finite, to get a compact surface. So what this picture represents, like here, this is what you would call a fundamental domain for the action. So here really it's like if I take this octagon thing and I have this group that's going to translate this octagon all around. So like this right here is another copy of the octagon. Like it's really hard to draw, but there's like infinite number of copies of the octagon in this picture. And the way that the octagon gets transformed by this group gives you a way to sort of glue the edges of the octagon together. So that's what this represents. Like these two edges are going to get glued together and these two edges are going to get glued together and so on. And when you do this, it's hard to see, but you can show that you'll get, in this case, you'll get actually a 2-hole donut. But when I draw this 2-hole donut, you think of it as like living in, like being embedded in 3 space, but it's a little bit deceptive because here I have a hyperbolic metric, and the hyperbolic metric descends to a metric on the quotient. And you can show that if you want to represent a hyperbolic surface as embedded in some Euclidean space, then you can't embed it in 3-dimensional space. It's impossible to embed in an isometric way a hyperbolic surface in 3-dimensional space. So this is not geometrically, this is not what the picture looks like. This is what it looks like topologically, but the actual way of measuring distances is different. So what's important about the hyperbolic metric for our context is that it has negative curvature. So I'm not going to give a precise definition of curvature, but kind of what it means in this context is something sort of about like, if I have geodesics, which are parallel, whatever that means, then it's possible for 2 parallel geodesics to stay close together for a long period of time, but then to suddenly diverge as you keep going. So in contrast to what happens in the flat case, so here I have 2 parallel lines and they stay close to each other the entire time. forward if I go forward in time or backwards in time. And here in negative curvature, I have two geodesics that kind of, when I go backwards in time, they kind of meet. You might say they meet at infinity. When you go forwards in time, they diverge. And that's sort of characteristic of negative curvature. Curvature in some sense is quantifying that rate of divergence. Okay, so now I'm going to say some stuff which maybe won't make sense, but I just want to try to, it'll connect to something later on just to show some analogies. So hyperbolic surfaces arise as quotients of the hyperbolic plane by some subgroup gamma. And in fact, sort of all of hyperbolic geometry can be rephrased in the language of group theory. So if you've seen like groups and quotient groups before, then this will make sense. Otherwise, it probably won't make sense. But you can realize the hyperbolic plane as a coset space of SL2R mod SO2. These are the special orthogonal matrices, 2 by 2. You can represent your favorite hyperbolic surface as this double coset space, where you kind of quotient on one side by SO2, the other side by gamma. And you can realize the tangent bundle, or really what's called the unit tangent bundle, which is basically the same thing, of your hyperbolic surface as SL2R mod gamma. And the geodesic flow is determined by matrix multiplication on this coset space by diagonal subgroups. So that may not make any sense, but really all I'm really trying to get at is that in the special context of hyperbolic surfaces, you can study the geodesic flow using group theory, really using this field of math called representation theory, which is really powerful. Okay, so now I want to talk about graphs. And really, at the end of the day, what I want to convince you of is that graphs are a lot like hyperbolic surfaces. So you've probably seen graphs before. It's just a collection of vertices and some collection of edges between the graphs. But I want to think of these as like geometric spaces. So I want to think that like all edges have the same length. Like this has length 1 and this has length 1, even though the way I've drawn them, they don't have that length. Just abstractly, all edges have length 1. On a graph, you can talk about geodesics. Geodesics are just going to be non-backtracking paths connecting points, connecting vertices. And on a graph, you can even talk about a geodesic flow and a tangent bundle. So it's a pretty, I mean, when you unpack it, it's actually a simple concept, but it's hard to describe in words. So you should imagine constructing this space, the space of all paths on a graph. So these are going to be like bi-infinite directed paths on a graph, together with a choice of sort of starting points. And so here, like, imagine I have some big graph, and here I have some infinite path on the graph, together with some sort of midpoint of this thing. Then my geodesic flow, for if I take one step of my geodesic flow, all I'm going to do is move my base point forward by one step. So here is a new point in my tangent bundle under the geodesic flow of this point. And you can show that if you have a graph for which the degree of every vertex is at least 3, then the geodesic flow is ergodic. But really, this is just a fancy way of saying that a random walk on a graph for which every vertex has a degree at least 3, in the long run, will end up being equally likely to end up at any vertex on the graph. So that's really another way of saying that the geodesic flow is ergodic. But I'm just trying to draw analogies with what we've already seen. So why does the degree greater than or equal to 3 condition matter? It's essentially because the degree being at least 3 allows for the possibility of branching. So imagine if you had a graph where the degree of every vertex was 2, then the only such graphs are going to be these infinite like straight line path graphs or like a cyclic graph. And in that case, your geodesics are boring. They just like travel in a straight line. There's no, if you start 2 different geodesics, they're always just going to stay close to each other forever. And that's kind of what this is supposed to represent. Like there aren't very many geodesics on a graph like this. If you have degree at least 3, then it's possible to have 2 paths that for a long time agree, but then suddenly, one takes a step in one direction, the other takes a step in another direction, and then they kind of become like decorrelated. Like it's kind of like just because you know what happens in one path doesn't mean you know what happens on the other path anymore. So they've started to diverge. So this is like parallel lines diverging, kind of. It's sort of the analog. So from now on, assume for simplicity that all graphs are regular. That means that the number of edges coming out of each vertex is the same for all vertices, and that degree of regularity is at least 3. So I've defined a geodesic flow on a graph, and I've said it's ergodic. So now the question is there an analog of quantum ergodicity in this context? So quantum ergodicity, a lot of the intuition came from quantum mechanics, but at the end of the day, it was a statement about eigenfunctions of the Laplacian, and it didn't require quantum mechanics to state. So on a graph, well, there is something called the Laplacian operator on a graph, and there's also something else called the adjacency operator. And on a regular graph, they're basically the same. They have the same eigenfunctions. So how does the adjacency operator work? What it does is it sums up the value of a function. So it acts on functions defined on the vertices. And what it does is it sums up at a given vertex the value of the function and all your neighbors. So if this is your vertex here, you apply the Laplacian. So I'm going to add up the value of the function at all my neighbors. I'm going to get -3. So if I apply the adjacency operator, then the new value at this vertex will be -3. And to find the values here, you'd have to know the value at other parts of the graph. But hopefully that's clear what this is doing. You should think that geometrically, this adjacency operator is very similar to what the Laplacian was doing. It was also looking at like the average value at neighbors. But if you have a finite graph, then the space of, so L2 of V, it's really just a fancy way of saying functions on the vertices, like ways of assigning numbers to every vertex. But if you have a finite graph, this is a finite dimensional vector space. So this matrix or this operator is only going to have finitely many eigenvalues and eigenfunctions. So it doesn't make sense if you just have a fixed graph to let the eigenvalue go to infinity. So what we instead consider are sequences of graphs which converge in an appropriate sense to the infinite regular tree. So what does this convergence mean? What I really mean is, imagine you have these regular graphs, they're getting bigger and bigger, and the way you're measuring the convergence is whether or not the length of the shortest loop in your graph goes to infinity. So you know on a tree there is no closed loop. And so you should sort of think, well, if all closed loops are really big, then you're close to a tree. And another way of also thinking about it is, so just like in the case of hyperbolic surfaces, in the case of regular graphs, every regular graph arises as a quotient of the infinite regular tree by a group of isometries. So like here's a 3 regular graph, and here's a tree, and this is the coloring of the vertices is kind of telling you how I'm going to quotient this one to get this one. But what's kind of interesting is like if I have a closed loop here, that will lift to a path here between vertices of the same color. So the fact that if I have like closed loops getting really long, that's like saying when I look at the tree and I color it according to the vertices, like how it gets quotiented, the path between vertices of the same color, the path between vertices of the same color is getting arbitrarily long. And all of this kind of fits into the framework of covering spaces, if you've ever heard of that or seen that before. But what does quantum ergodicity on graphs mean? Okay, so in a rough sense, what it's saying is if you have a large regular graph, then on average, eigenfunctions of the adjacency operator are equidistributed. So what equidistributed means in this case is that, so if you have an eigenfunction of the Laplacian psi, and if it's normalized so that like its L2 norm is 1, that means like if you add up the value squared at each vertex, you get 1. If the function is equidistributed, then it should have roughly the same value at every vertex, but there are, if there's n vertices, then that value should be 1 over n. So that's what this is saying, that the norm squared of the function should be roughly 1 over n for most vertices. A more precise statement is that if you have a sequence of regular graphs which converge to the tree in the sense mentioned above, and then for each graph, you choose some subset of the vertices, call it Rn. And every graph has its own collection of eigenfunctions, which I'm going to call the psi jn. So this upper n is telling you these are the eigenfunctions of gn. So here I wrote this expression. I'm going to break it up into pieces. So this quantity here, I'm summing over the vertices in my region of the norm squared of the eigenfunction. So here I kind of wrote an interpretation, a quantum mechanical interpretation. This is like the probability that the jth stationary quantum particle on the graph is observed to be in Rn. This here is the probability that a randomly selected vertex is an Rn. It's just the size of Rn over the total number of vertices. And I'm looking at the difference between those values. So if it's equidistributed, that difference should be small. And here, sort of for technical reasons, there's a squared, but it doesn't really matter. And then I average over all quantum particles, namely over all eigenfunctions. And I want that quantity goes to 0 when my graphs converge to the tree. Okay, so hopefully that made some sense. This is not my theorem. This is an already existing theorem. But now, the last thing I want to talk about is I kind of want to connect graphs to hyperbolic surfaces. So here I have these two suggestive pictures that suggest that there's a relationship, or at least there's heuristically a relationship. This is some sort of tessellation of hyperbolic space. And this is a picture of a 5 regular tree, but they're sort of drawn in a way that shows, oh, they kind of look similar. Okay, so here's something interesting that I don't really have time to do justice for, which is the p-adic numbers. So imagine you have a tree where the degree of regularity is p+1, where p is a prime number. There's this field called the p-adic numbers, which has a definition, which I wrote here, but this may or may not make any sense. So on the rational numbers, we have the usual way of measuring distances between numbers, but there are these more exotic ways of measuring distances called the p-adic norms, or p-adic absolute values. And essentially, a rational number is considered small if it's divisible by a large power of p. So this is the formula. You can write any rational number in this way, and then the size of this thing is p to the minus n. So if this n is big, then this quantity is small. These groups of numbers form a field. So that means that you can add, subtract, multiply, divide, and you can form matrices with entries in this field. And again, you can talk about, oh, is the determinant of this matrix 1? So again, you'll get this group, SL2QP, the 2x2 matrices with entries in the p-adics whose determinant is 1. And it turns out that SL2QP acts on the p+1 regular tree, just like SL2R acted on hyperbolic space. And again, similarly to before, we know that all p+1 regular graphs are quotients of the p+1 regular tree by some group of isometries gamma. And here, this is going to be totally analogous to what I said about hyperbolic surfaces, which may or may not have made sense. So the tree, it turns out, can be realized as a coset space, SL2QP mod SL2ZP, whatever that means. SL2ZP is the set of p-adic numbers with absolute value less than or equal to 1. What's kind of strange about this is a compact group, just like before this was SL2R mod SO2. SO2 is also a compact group, so you kind of have this big group mod compact group. Finite regular graphs can be realized as these double coset spaces, just like as before. This is a slight lie, but essentially the tangent bundle of the graph can be realized as this coset space, and the geodesic flow on a regular graph, again, is given by multiplication by diagonal matrices. So again, maybe this may not make any sense, but the point is it's completely analogous to what happens for hyperbolic surfaces. And well, as you might expect, the group theory of SL2R and SL2QP is very similar. So there are a lot of analogies between hyperbolic surfaces and finite regular graphs. And kind of the point I want you to take away from this is that what's nice about this is if you're trying to prove a quantum ergodicity result, but you're working with these spaces that are so closely connected to the group theory of some really nice group like SL2R, SL2QP, it gives you all these new tools to prove these results, namely coming from representation theory, which is a really powerful branch of mathematics. Okay, so now the last thing I want to say briefly is what I'm working on. So in general, if you have a group, there's sort of a way to construct a geometric space out of it so that that group acts by isometries. So we saw before, if you have SL2R, you get hyperbolic surfaces. If you have SL2QP, you get regular graphs. If you have SLNR, n by n matrices with determinant 1 with real entries. The things you get are called symmetric spaces. And if you work with SL and QP, the spaces you get are called Bruhat-Tits buildings. And so I'm working on proving quantum ergodicity type results for Bruhat-Tits buildings. And at the end of the day, the tools used are really coming from representation theory, but the intuition is coming from quantum mechanics. And the last thing I want to show is this mystifying picture of a part of a Bruhat-Tits building for SL through QP, and I'll end there. There any questions?
Can you explain more about the last part that you've shown us?
This picture?
Yeah.
Yeah, so it's not easy to explain, but you know, because I didn't explain to you how, like I said up here, that this SL2QP acts on the regular tree by isometries. But what's really going on here is this may or may not make sense. So this you can build a vector space over any field. So over the p-adics, you can build vector spaces like just like you can build Rn, you can build these vector spaces like QP to the n. And within these vector spaces, so inside of, for example, inside of like Rn or like R2, you have these things called lattices, which are kind of these discrete subgroups that are closed under addition. And in the language of math, we would call those Z modules, where Z is the integers. So inside of QPN, you have these things, you have what are called ZP modules. So you should think of this as analogous to lattices inside Rn. And on these collections of ZP modules, you have an action of this group SLNQP. But the way that the topology of the p-adics is like everything's very combinatorial. So on these lattices, you have these incident relations. So like if you, well, like, I don't know, this might be hard to draw, but like, you know, if you imagine inside of Rn, I have lattices. Like here, I could imagine drawing like an integer lattice, but inside of this lattice, I have sublattices. So I have, for example, if I just take these points, this is going to form, for example, a sublattice inside of this lattice. And so kind of the way that these buildings are constructed, it's like incidence relations on lattice, these ZP modules, which you should sort of think of as like analogs of lattices inside of this p-adic vector space. But what it gives for you is this combinatorial structure. And but the combinatorial structure is like, this picture is kind of mystifying, but you can kind of decompose the space into easier to understand pieces. But it may be too hard to really properly describe that. I mean, this picture is hard to understand for sure. But it's hard to find any picture of anything resembling a building other than if you search Bruhat-Tits building, you're gonna get a bunch of pictures of trees. Okay, but if you want to get a sense of the higher dimensional versions, it's really hard to find any pictures. I don't know if that made any sense, but to really understand it, you kind of have to understand how the p-adic numbers work, which I didn't really explain.
Thank you.
I'm not really super familiar, but I was wondering what sort of tools you have to pull from representation theory to attack these.
So, yeah, so I mean, representation theory is, right, it's the study of like representations of groups. So really it's like, there's a general theory if you have a group you have what's called the regular representation of a group. So if G is a group, you can consider well, so groups have what are called Haar measures. So every group has a Haar measure, and that allows you to talk about L2 functions on the group. So you can consider L2 of G. So these are functions on the group. And this gives you a representation of the group. So G gives a representation called a regular representation. And the way this works is like if you have a function and you have a group, then the group sort of translates the functions. So for example, if your group is like R, you consider functions on R, and then the way that R acts is essentially just translating the function. But this is a more complicated version of that. But in general, if you have a group, you want to decompose it into irreducible subrepresentations. So in the case of the regular representation, you want to decompose it into irreducible representations, but the technicalities of what that precisely means is a lot more complicated. Because you no longer have the notion of like direct sum decomposition of irreducible representations. It's called a direct integral decomposition. But the thing is, for these groups in question, the regular representation, the irreducible subrepresentations that show up inside of it have been totally classified. And similarly to here, in general, if H is a subgroup, then G acts on L2 of G mod H. And as I said up above, and you can kind of use the decomposition of the regular representation to understand these other representations. But as I said up above, all these spaces, like the tree, for example, is itself a coset space. So it's a group mod some other group. And so functions on this space, you have a group action on that space, and you want to sort of decompose that. And just like this is also a coset space, and so representations on this is a representation, and you kind of want to decompose that. And if you can decompose it, it gives you a lot of information. And in fact, like the decomposition is very closely related to the eigenvalues of the adjacency operator on the corresponding graph. I'm essentially using the fact that people have figured out like how to decompose all of these representations that are relevant for these geometric spaces, and trying to leverage that. And then there's also, it's intimately related to the eigenfunctions of the Laplacian or of the adjacency operator, but there's a lot of steps to get there, but I don't know if that answered your question.
Thanks.
Yeah.
I'm also really new to a lot of this stuff, but so this might be a nonsensical question, but is quantum mechanics definable on manifolds that have zero or positive curvature because of this ergodicity thing, or is it more just like an analogy?
So it's totally possible to, like, I would say quantum mechanics is still definable. The issue is like quantum ergodicity is just a kind of, there's a general field like, so in mathematics, there's a field called, or there's sort of two fields that are very closely related. One of them is called semi-classical analysis. The other one's called micro-local analysis. And a lot of these fields, what they do is they use ideas from quantum mechanics to prove results about PDEs. And this quantum ergodicity is just like one small corner of that world. But in general, because like this procedure of quantization I described, that's really the subject of micro-local analysis. So that can be done on any manifold. Yeah, so where did I talk about this? Yeah, so here I talked about this procedure on any manifold. Again, so on any Riemannian manifold, you have like the Hamiltonian formalism, that generates the geodesic flow. That doesn't depend on curvature. And you have this quantization procedure that sort of allows you to reinterpret classical observables as quantum observables. They become self-adjoint operators. And that works on any manifold. And again, like the Laplacian, it's true on any manifold that if you quantize the like kinetic energy Hamiltonian, that you get essentially the Laplacian, and the Laplacian makes sense on any manifold. So all of that's curvature independent. Really, the only thing that depends on the curvature in this case is the ergodicity pieces.